have a quick announcement and then more from me, but go ahead.
Hi guys, I'm Dale Cook. I am the co-founder and president of the Women in Science and Engineering Club. And it's not just for women, just first of all. I know it says women in the name, but it's just to represent and support minorities and women in science and engineering. So really it's for everybody. It's just, we just do like workshops, like how to write a resume for science majors. We had it last semester, and it was really successful. We have a professional come in from the Career Center, and they come in and you bring in your resume and we actually talk about it. We have guest speakers. Hopefully, I'm hoping for a cosmologist, or the head of the cosmology experimental lab at UCSD to either come talk to us or we'll go out there. He took pictures of the remnants of the Big Bang, and he took the first pictures of it. And so he's a very successful scientist and very a good contact. So anyways, we're going to have other workshops going on, but if you're interested, write your signature and print it and your pay number. And if this runs out, just I'll give you another piece of paper. You can come talk to me afterwards. But anyways, our first club meeting is tomorrow from 12:45 to 2. And if you guys know where the mural is on the main campus, or in front of the main cafeteria right here, we'll be on the lawn right adjacent to that. So just you can see us there, or I'll send out a reminder email as well. So, yeah.
Right. Thank you. All right, well, I probably don't need to tell you, but I feel like I should nonetheless. 1 week from today, what's happening here in class? Right, you got your first test coming up. All right, so as you know, we've been working towards this. I've been saying hopefully you're working in chapter 4, and hopefully you've gotten to the point where you've gotten stuck a few times, if not maybe at least once. Hopefully you're there now where you did enough work between last Monday and today that you go, I'm kind of stuck again here. And so hopefully by me doing some more examples, you'll get some more insight. So as you know, on Monday we spent the whole day doing examples. We followed that in lab with, I think, a good example of shooting that little ball, and watching some of you do the calculation, I can tell there was a lot of learning going on. You're like, okay, that's how you get the time. Oh, that's why it's positive. Oh, that's why it's negative, you know. And just those little problems that you encountered, and eventually, of course, hopefully you calculated it right, and the ball hit the target, or at least got close to that target. If you measure things really diligently and then do the calculations, it usually hits, but you got to have perfect measurements and perfect calculations. And I didn't necessarily expect the perfect measurements, but definitely the perfect calculations. Well, anyways, I hope those examples help. I'm going to do the same thing now. I'm going to jump right into where we were, or where we left off. On Monday, I said, hey, let's do 2 examples of an object going in a circle. We did 1. Let's do the second one. I think a little harder one too. And then we'll jump back to some other examples. I suspect we'll get all done with that, and then I'll go into chapter 5. So I've got a few things set up for chapter 5. Actually, I might be missing my hockey puck. Maybe I'll go get it, or maybe I'll just deal with it next time we have the lecture. But it's a good demonstration of Newton's first law of motion, and probably best is just to stay focused on chapters 1 through 4 here. So we'll see how far we get into chapter 5. There's no real rush into chapter 5, although I do know this, that if I say a little bit about chapter 5, that will jog your memory of chapter 5, not really give you any new information, just to remind you of Newton's 3 laws, and that kind of sets the stage then after the test to really plow into new stuff after there. So that's kind of the goal here. But that aside, it's the chapters 1 through 4 that obviously you should be most focused on and most concerned about, and rightfully so. So that's where I'm going to go with this. You know, stop me if you have any questions so we can work on it. Obviously Monday is a holiday, so there is no class. That's why I said the next time I see you, even though it won't be for a whole week. Okay, and so we've got that long 4-day weekend coming up. Friday's a holiday and Monday's a holiday. But you may be interested. I asked Don to write it here on the board. Even though Monday is a holiday, I would encourage you to come to school anyways. Holidays don't exist for students. You shouldn't be having a holiday. You should be steady, 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 steady. In fact, I'll tell you my life story. I remember after graduation, and my first job was with McDonnell Douglas, and we were doing some optics stuff. We were putting a satellite, and we had to adjust it, and it was pretty straightforward stuff. But you know, we'd go in there each day, take a picture from the satellite, and we'd have to calibrate it. We were trying to be able to focus on a double yellow line, you know, from 300 miles up, and try to resolve those two double yellow lines to see if you could see the black strip in between it. And that was kind of our goal, so we were working on that. And like I said, so I graduated in May, started working. 4th of July comes around, and I got up on the 4th of July and go, wow, this is a holiday. What do you do on a holiday? And so for 8 years before that, holidays meant study time. Well, I didn't have any study time. I was kind of lost there for the first morning. So I finally found a friend who had a bike, and I just kind of discovered the beach and the boardwalk and went for a little ride there. So that was fun. So anyways, all that to say is you shouldn't discover the boardwalk yet. You're way too young. You should be study, study, study. And this is that opportunity. So come to campus, come to 1 to 4. We'll have a little review here on Monday, getting you ready for the test on Wednesday, okay? So, and someday you will graduate, and you will have the 4th of July, and go, hey, wow, this is kind of nice. I like holidays here, all right? And that's what holidays are. Anyway, so I think you get the idea. Do want to just remind you of the test and preparing for the test, besides, of course, today and on Monday. When you come, prepare to get started right away. Just, you know, come in and either A, turn in your chapter 4 when you come in and put it here, or leave it in your notebook. But I want to give you the full amount of time. I hope nobody needs the whole amount of time. I hope you come in and you find the test straightforward and easy. There'll be 5 questions, and I hope I'm just going to pass it out right at the beginning at 5 till. You got the 2 hours, 5 minutes, and unfortunately we got another class, so we got to, you know, that's all the time you get, and then we're going to have to just call it quits there. And so hopefully you won't run out of time. But if you get stuck on one, that happens, and so that's why I want to make sure you've got all that time there. One problem on the top: no notes, no cheat sheet. Yes, you can have a calculator, but no notes. Yeah.
Not that we need it, but would you be here a little earlier too, just when we get started, or?
Oh yeah. I can't start you early. Is that what you mean?
Yeah, that's what I mean.
No, I need a Yeah, too hard to keep track of when you start versus stuff. And you'd be interrupted anyway if you started now and people were coming in for 5-10 minutes. Yeah. But the test really is not a time pressure usually. You know, there are some people get stuck and run out of time, but it's not generally one of these times. I know some tests you just didn't have enough time to do it. You worked as hard as you could. You never got stuck. This won't be that way. You only run out of time if you get stuck, if there's something you don't know. I mean, it's 5 questions.
Right.
Yeah. So, and just like the homework. I do want to emphasize then, as you are getting ready, here's the solutions to chapters 1 through 4. Before I walked into class, I posted the solutions to chapter 4. So they're there. Okay? Now, don't use that as a crutch and say, okay, I don't even have to do chapter 4. I'll just copy it off the website. Okay, you're doing yourself a disadvantage. Try chapter 4. Work on chapter 4. Okay? There may be times where you can't get the right answer here, but I would say don't give up right away. Try it again, ask me questions, ask Don questions, call your friend, you keep working on it. But at some point, you may need to go and rely on the answers that are posted online. If this is 3 a.m. and you're studying, it's the day before the test, that would be a good time to go online, because nobody else is going to answer it. You're probably not going to figure it out. You need some extra help, and that's what this is for. And so chapters 1 through 4 are there. 1 through 3 were already there. You've turned in chapters 1 through 3 already, and like I said, you just got chapter 4 to do. Which reminds me then of this last thing is right here. Here are the homeworks and labs you've turned in so far. So let me get back what I can. here, the first bundle is chapter 1, and so I will grab chapter 1, and it's kind of useful to just put it at 90 degrees and place it in here and flip through it and find it. If you don't want to take in class time to find it, I completely understand. I mean, after all, you know, you wouldn't want to be interrupted in a movie. Why would you want to be interrupted in a physics lecture? So I understand that you don't want to be interrupted. So I'll throw these out into the lab, and as you go to the lab, you can collect them either now or later or sometime through the semester. You probably noticed a big pile on the side. Those are from last semester. So now that I'm starting to pass back papers from this semester, I'm going to put all those in the recycler. So they'll just sit over there all semester long. And so if you don't get chapter 1 until 5 weeks, it will be there. Okay, if you don't pick it up till August, it'll be there. But about August 30th or September 10th of next semester, then I'll recycle them, okay? So that's where they'll sit. And here is lab number 1 that you have. Obviously, chapter number 3 that you just turned in Monday I don't have for you. But other than that, I think I've got all the stuff for there. As you scan through it, hopefully you'll see 15 written across the top. That's how I asked the grader to grade it. Not correct it right or wrong. We'll find out if you know it right or wrong when you take the exam. That's what the exam is for. But this is just to see, you know, are students, you know, putting in what will help them. And so the points are given on, you know, a good, honest effort. Did you put that effort into doing it? And that's the idea there. All right, well, unless you have questions, shall I jump into number 30? This is the second one going around here. All right, let me read number 30 for you. If you don't have the book, I'll draw some pictures. And like a lot of problems, the author could have done a little bit better job here. He could have given you a better coordinate system, but I think since he doesn't, he's referring to the traditional coordinate system. So I'm going to start off by just putting the traditional coordinate system and saying that I think this is what the author is referring to. Watch. Here's number 30. It says, a ball swings in a vertical circle at the end of a rope that is 1.5 meters long. Okay? So far, I have this. I've got a circle, a ball on the end, spinning around, and as it says, it's a vertical circle, so it goes around and around and around. When the ball is 36.9 degrees past the lowest point and on its way up. Okay, so the lowest point would be here. They say 36.9 degrees. But I suppose at this point, I don't know which way, left or right. It does say on its way up. So if the ball is on this side, it would be clockwise motion. If the ball is this way, I guess it would be a counterclockwise motion. Yeah, it doesn't say counterclockwise or counterclockwise, but it does say this. And this is why I said, if he's using the traditional coordinate system, which would be my assumption here, we can figure out which one it is here in just a second. So when the ball is 36.9 past the lowest point on its way up, the total acceleration is, and so a vector, and he gives it in the components. It's negative 22.5 in the I-hat direction, and 20.2 in the j-hat direction. So if I were to draw that vector on our traditional coordinate system, what would it look like? What quadrant would it be in? Yeah, so it would be negative 22 and positive 20. So that would be what the acceleration vector would look like. And this angle here, I suppose I could find it, and maybe I should. I will, why not? But I know it would be less than 45, don't I? Because this is 22 and that's 20. So let me go and find that. And so we'll get an idea of that angle. And that angle would, I guess, be the inverse tangent, and I will go opposite, so that's the 20.2 over adjacent, that's the 22.5. And so give me some kind of idea of the angle. And now that I switched calculators, I better check the mode. How good I did. It was in radians. Glad I checked. All right, back to degrees here. So inverse tangent of 20.2 divided by 22.5. And so roughly 42 degrees. So there is our direction. Okay? Now, moving on with the question, or maybe they give a little bit more information. No, it says, at this instant, A, sketch a vector diagram showing the components of the acceleration. Well, I guess I have kind of done that as I was getting this far. B, determine the magnitude of the radial acceleration. And C, probably the hardest part of all, what is the speed and velocity of this ball? Okay, so let's put these two together. Maybe I'll even change colors here so I can put the acceleration vector on here and not to confuse it with the others. I say that this would tell me which one the ball is, right? Which one is this? Could the ball be here and have this acceleration? No, why not? Yeah, I need it going towards the center of the circle. And actually, maybe it would have a small component going towards the center of the circle. So maybe it's not as complete. Maybe I'll try both. But I'm thinking, even though the author wasn't as clear, maybe I'll go back. Does he say counterclockwise anyways? A ball swung on a vertical rope? No? Sure would help. But I really think the author intent is for this one to work out. And not even the intent is to make you think which one it is. But maybe it is, and I'm missing something here. But if I were to put the grid on here, something like this, this vector, which is angling up at 42 degrees, would look like something like, maybe I need to put this angle in here. What's this angle here? Yeah, so if this one over here is about 37, right? Doesn't that make that one about a 53? Okay. And so it's the 53.1. In fact, I think that's the same angle as the 3, 4, 5 right triangle. I don't know if he wants us to notice that or not. But that's about 53. And so as I come over here and draw in green the acceleration vector, noting that it was 42 up, it would be something like this. Fair enough? If it was over here, maybe we should take a moment and say, well, what would this angle be? I guess that would be 36.9. And so 42. Huh. I was kind of hoping it would be lower than that, because what I do need to know is, wouldn't this acceleration vector have to have a component towards the center of the circle? I mean, that's the whole idea of turning. And so if this vector had been below this, then it would be turning that way. This vector seems to indicate that it would be speeding up and turning. This vector indicates that it would be slowing down and turning. Oh, and maybe did they say it was slowing down? The ball is at the lowest point on its way up. When the ball is at its lowest point, they don't really say it's slowing down either. Bummer. Again, more of the same. I suspect the author is thinking about a ball going around in a vertical circle, and because of gravity, it would be slowing down. So more of the same here. So unless I'm missing something, I'm not sure we can completely rule that out, but I think this is what the author wants. This would have to be going at a huge speed here. And maybe we'll come back and look at that, and maybe there's something else there that I'm missing. But I really think your author wanted you to take this picture here and go through these steps of radial acceleration and tangential acceleration. And so, like I said, this one would make it turn and slow down. This would make it turn and speed up. And the amount of turning would be very small compared to the amount of speeding up. So let me stay focused on this one, at least for a moment here. Because putting that acceleration vector here, this is the part here where it says determine the magnitude of the radial acceleration. Do you see that in here? And we haven't done any problem like this at all. But it is about geometry, and it is about finding components. So we can use, hopefully, some very useful information from chapter 3 here. And that's why I said, if you could do chapter 4, you probably could do chapter 3 and chapter 2 and chapter 1. And so this is a tough one. How are we going to get the radial component? Maybe I should draw it first, right? I mean, what would it look like? What are you really saying? So I'll draw it in blue, but if this green one is the acceleration vector, what you're saying here is the acceleration vector can be made up of this part, which is blue, and then this part, which is perpendicular to the blue, so tangential, right? Now, I need to be careful on the part that I know. Remember how they gave it to me. They gave it to me in Cartesian coordinates. So what I know is this orange. I know the x and I know the y. All right, so maybe now you see it in the picture. How are you going to get the radial one? Yeah, first of all, let's find the magnitude of the green one. Then we can take a component of the green one to get the blue one. I need the orange ones to be put together to get the magnitude of the green one. So I'll start there. These are the orange one. So to get the magnitude of the vector A, I've got to take these two components here, the 22.5 and square it, and then the other, the 20.2 and square it, and I'll take the square root of that. So looking, like I said, at these orange ones, which are the Cartesian coordinates of it, I would get the green one. Now that I have the green one, I can look at this triangle laid out in blue, and what I would want to know is how much of this blue one is part of this triangle made up by the green one. So I would take the cosine of this angle here, right? So I would take this magnitude, 22.5 squared plus 20.2 squared, and multiply it by cosine of yeah, we just said the whole thing was 53.1. Earlier on, we said that part was a 42, so I'll subtract the 42. And we've got 11.1 here. So this is 11.1 degrees. And that would then equal my radial component. You see that in the picture? Okay.
Did you find the angle again?
Which angle? I got a lot. The 11?
Yeah.
All right. Let me blow this picture up here. Okay. I've got the orange vector. That's horizontal. That's this one here. Okay. 22. All right. Then I've got the green one in that picture. That is the direction of the acceleration. That I got back here when I did this inverse tangent. So that angle is 42. But I also have then this blue one. The blue one is along the radial part, which I said was 53 degrees. I got that because of the 36.9. That's got to be the complement of it. So this whole angle here is the 53.1. So this angle there must be the difference between them. So I take the 53 minus the 42, get 11.1. All right. It's clear as mud, right? All right, so again, it's one of these things that we haven't done it before. Could you do it on your own? And hopefully you'll see. There's nothing that I didn't do there that you haven't seen before. Just maybe we haven't put it all together in one problem. And hence, this is the idea of the physics class. There's the syllabus, right? Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. So we'll put those together there and answer that question. What is the radial component? And they actually asked for a number, I think, here. Determine the radial component. So let me put that into the calculator here. So 22.5 squared added to 20.2 squared, and take the square root of all that, and that's about a 30. Multiply that by the cosine of 11.1, and we're at about a 29.7. So if I do my math here, the radial component is about a 29.7, and this is another good example of, well, I didn't put the units in, but I hadn't forgotten them. They're in my head, and I'm working with them in my head, and I want to put them in the answer, even if I didn't put them along the way. Part A was just write the components of the acceleration. So this is it, and this is part B. So this is part B. Find the radial component. And really the purpose of finding the radial component is what we needed for C, where C says, now determine the speed and velocity of this object. So how are you going to get speed? Right, and that's what we worked out for this class, that the radial acceleration is v squared over r. And so now that we've got the 29.7 meters per second squared for the radial component, and we're given that the ball is making a turn or a circle of 1.5 meters, the unknown is the velocity, or speed, I guess. We've got to do a vector here to get a velocity, but the speed here. And so I'll take that 29.7, multiply it by 1.5, and take the square root of all of that, and I got about a 6.67. So 6.67 meters per second then is part of the answer. That's the answer I get for the speed. Now, to get a vector, I've got to have a direction with it. And the author wasn't specific, so I could either just give its magnitude and direction, which I'm tempted because that's going to be the easy one, or I can put it in its components. And maybe I should do both for you so that you could do it either way. But if we go through our geometry here, just like we got this angle here to be 36.9, it would come out the same way. Maybe I should draw a picture, but remember, there's the radial one. And if I draw then the velocity vector here, that velocity vector has to be perpendicular. And so, if you are looking for this angle, you hopefully remember from your geometry, the whole thing is 180 degrees. And so if this part is 90, then this part, which is 53, and this part have to be 90. They have to be complements of each other. Well, just like these have to be complements of each other. So this has got to be the 36.9. So 36.9 plus the 53.1 is 90 degrees, plus the right angle make a whole thing 180 degrees. So that's how I get the 36.9 degrees, just like I got it here. So one of the answers to answer this question is when you can say velocity vector, you could say it is 6.67 meters per second at an angle at 36.9 degrees, and I suppose from the positive x-axis to be more detailed here of what angle are we talking about. And that would, I think, technically answer his question. I think, though, he really does want an x and a y component, given the fact that he started the problem with giving you acceleration in the x and y, the I hats and the j hats. So why don't I go that route too and say, all right, what is the velocity vector? And so it would be a magnitude of 6.67 meters per second times the cosine of 36.9 degrees I hat, right? And as you're looking at this velocity vector, you would want to know how much is in the x direction. So there's the cosine of 36. And then the vertical direction would be 6.67 meters per second times the sine of 36.9 degrees in the j hat direction. And so that's how I'd get it into its components. And so if I actually then put this into my calculator to get a number, cosine of 36.9 gives me 5.33 meters per second. The I direction, 6.67, times sine of 36.9 comes out to be 4.00 j hat. So that's what I'd get if I wrote it out into its I hats and j hats. And boy, I don't know why I don't ever use this calculator. I really like it. Maybe part of the reason I like how clean it is. The buttons are clean. There's not, fingerprint scum all over it. They're real spongy, nice and black background. Oh, anyways, but there's the problem. A little more sophisticated than the last one, right? But reasonable, I hope. Can handle that one. Good. Looked like you were asking a question.
Yeah. So what is it that they wanted to find? Either one of those?
Yeah, well, the question says find the speed, there it is, and the velocity.
Yeah, but I mean, for that, the velocity, because you have two.
Right, and so either one I think is a correct answer. Yeah. I do think he's looking for this one because in this form is how he gave the problem. So I suspect he's really looking for this. But if this was a test, I certainly would give you full credit for either answer. I mean, I asked for velocity, and I didn't say, it has to be written in the Cartesian coordinate. That's magnitude and direction, that's magnitude and direction. That's all. All right, well, like I said, wanted to do one more with circular, so you've done two. And then let's jump over and do some more projectile ones here. And so I've done 3 projectiles, now 2 circular ones. I'll do 2 more projectiles, and then really the only thing I can do now is let you do them. I mean, there's not really much more I can do. It's like, look, I've done them, I've shown them, and now you just need time. And it sounds like many of you have heeded that time that, you're not going to try to all learn it in one day. You're going to do a little bit each day. So I've been warning you about that. And it's still 7 days away. So, take little pieces, little steps as you go along. So the next one I have on my list is 55. 55 is I think a fun one too. It's again 2 dimensions. It's a projectile. It's got 2 objects in it, so I think it's a little harder, and it's got some angles in it. So it makes a good example here. It says this. It says a hawk is flying horizontally at 10 meters per second in a straight line, 200 meters above the ground. A mouse that it has been carrying wrestles free from its claws. The hawk continues on this same path for about 2 seconds before attempting to retrieve its prey. To accomplish this retrieval, it then dives in a straight line at a constant speed to recapture the mouse in midair 3 meters above the ground. All right? So again, read it all the way through, got a good gist of it, come back and draw some pictures. Probably not a very realistic problem. I can't imagine a hawk waiting 2 seconds before it decides to retrieve its prey, but nonetheless. And I can't imagine it going in a straight line, and I can't imagine it going in a straight line at a constant speed. So perhaps not realistic, but it does make for a nice problem. 2 objects, motions involved, and the simplest motions we can give you. Straight lines, constant speed, dropping, and all those. In fact, hey, tell you a little story. It reminds me, a very similar episode happened near my house. Although it wasn't a hawk, it was a crow. And it wasn't a mouse, it was one of those big alligator lizards. You know those ones I'm talking about? Real sharp, snappy jaws. 'Cause I'll never forget it. I was doing yard work, and all of a sudden, it just falls out of the sky. And I don't know if it came loose, like if it, bit the crow, and the crow dropped it, or if the crow was trying to kill it and drop it, but just aimed right in the middle of the street. Anyway, this thing just comes tumbling down. So I'm all working. Something's going on. I'm like, what's that? Anyways, my neighbor sees it, retired gentleman, and at that time my kids were really small, and he thinks my kids would love to see a lizard. So before the crow can come down, he goes tearing out there and goes, "Hey, kids, come here, you want to see a lizard?" So we kind of go over there, and he grabs this alligator lizard, big thing too. I mean, this was going to be a feast for the birds, and he pulls it over to my kids, and they go, "See, look!" And that alligator lizard turns around and just ripped the skin about a centimeter across. I mean, blood shooting all over the place. My 3-year-old screaming, "I don't want to see a lizard!" running into the house. So every time I read this problem, that's all I can think about is this lizard and my neighbor and the blood going everywhere here. All right. So, but this one the bird catches. This was a little different. So drawing this picture, here is, I'll call the path of the hawk. It's way above the ground, 200 meters up. And, I got to draw a bird, huh?